sometimes life is, well, unpredictable. And sometimes things just seem to be the way they were supposed to be. What you see on the screen is a trace of a pentode vacuum tube. It is being displayed on a Tektronix model 570 characteristic curve tracer. So what do those two have? How do I tie those two together? Well, I wanted to return to, I wanted to make one more video, and I wanted to return to electronics if I could. As many of you know, I've been off doing some kind of wrapping up a review of my astronomy hobby and things like that. But my second love, chronologically that is, was electronics. I started out with astronomy and chemistry because I got a telescope and a chemistry set when I was 9. But by the time I was in middle school, they called it junior high back then, electronics was the thing that I loved the most. And of course, being in the 1950s, that meant vacuum tubes. Well, a couple of weeks ago, my UPS delivery man stopped me. I was out in the front yard as he was delivering something, and said, "You're interested in vintage electronics, tubes and things like that, aren't you?" And I said yes. I wondered why how he knew that. Turns out he has delivered so many things to me that he knew it. And he also had a background in electronics. He had worked for Raytheon back in, I think, in the 80s, doing some electronics work. And so he said, "You wouldn't be interested in an old Tektronix curve tracer, would you?" I mean, my eyes lit up. It was like, you know, it would be like asking Albert Einstein, I'm no Einstein, but like asking Albert Einstein, "Would you be interested in relativity?" Yeah. So he sold me this curve tracer, and I've been playing with it for the last week or so. And so it is, I think, fitting as a video return to electronics. And so, you know, if I had to close out on anything, this would be it. At any rate, enough about me and the history and my UPS man. What this device does is it displays various current and voltage characteristics graphically. Along the vertical axis, it displays the current through the tube, and along the horizontal axis, it displays the voltage. In this case, it's the plate current versus plate voltage. And the steps are varying grid values. So let me show you the block diagram of this device, and then come back and show you how it works a little bit. And then we'll run a couple of tubes on it and see how it works. Now, it has a neat feature that it allows you to switch quickly between one tube and another tube. I'll save for later what those tubes are, but these are two pentodes that are being displayed, and you see there's a difference in that one and in that one, though there's not a lot of difference. Notice that the top is very close to the top trace of this one. So let's take a look at a block diagram. So here is the block diagram of the Tektronix 570. By the way, this device was built in 1955. I was 10 years old. On the left is the shaper for the stepping voltage. You remember you saw that it would step the grid voltage. It starts with this stepping voltage shaper that feeds a step generator. Then that is amplified by the step amplifier and can be applied to the grid of the tube. This is the device under test. And there's space for two of these so that you can switch between them. We'll look at that in a little bit later. For the display we just saw, the step is applied to the grid. The cathode is grounded. The plate is connected to the horizontal amplifier and also to the plate sweep generator. Now, what the plate sweep generator does is it generates a sweep voltage that can go up to, I think, 500 volts on the 570. So it can be anything as little as 1 volt. Let's see, it's 5 volts. It's the traditional Tektronix 2510, so it's 5, 10, 20, 50, 100, 200, 300, 500 volts. So it applies that to the plate, and then you can read out the plate through the horizontal amplifier while the current through the tube is measured by the, vertical amplifier. And the way it does that is the current through the plate sweep generator, it flows through this resistor. And so it taps the voltage off of that. So this allows you to measure plate current on the vertical while measuring plate voltage on the horizontal. And that's the display we just saw a minute ago. So this is the basic diagram of the 570. So this is a printout from the 570 manual showing the plate current versus plate voltage. And in this case, this is for a 6U8. Now, a 6U8 is a two-section tube. It looks like this. Notice that one section is a triode and one section is a pentode. Let me just pick that up and take it a little closer to the camera so that you can see a little better what that looks like. So you see that it's a triode on the right and a pentode on the left. These tubes were used in early television sets to generate the vertical sweep. The triode section was used for the oscillator, and the pentode section was used to drive the yoke. I'm not going to get into television theory here, but basically that is the way that the signal would be swept across the screen from top to bottom. There was also a horizontal sweep system that would sweep it from left to right. So what you see here are a series of steps, and on the left are the setups for this. So in the manual, one of the things that part of the training of someone on using the 570 was to set up a 6U8. And by the way, it even, I think, originally came with a 6U8 tube. Fortunately, I have some new old stock tubes and was able to dig up a couple of 6U8s, but the basic idea of this is it allows particularly a design engineer to measure the characteristics of a particular type of tube. It also allows someone to compare the characteristics of two tubes. For example, suppose that you have a dual triode, like a 6SN7, where there are two triodes in the same package. Well, you can switch between those two using the switch that I used earlier and compare to see how well matched they are. So there were basically two applications for this device. One was for design engineers who were designing tube circuits to be able to find out the characteristics of the tubes they were using so that they could design the circuit around those characteristics. And the second, which has come into even much more use these days, is the matching of tubes. Because of the resurgence of vacuum tube amplifiers, both for guitars and for high fidelity, the need to match tubes, particularly since you're dealing in many cases with new old stock tubes that have been around for 50, 60, 70 years, is finding a pair of tubes, for example, that have similar characteristics so that they don't require a lot of imbalance in the amplifier to work correctly. So, for example, in a push-pull stage, output stage, and if you want to know more about that, there are some videos I did on how tubes work and vacuum tube circuits that you might want to look at some point. But at any rate, these days, these are used by places that specialize particularly in tube electronics, generally amplifiers, to match tubes and do other things. For me, it's just a toy. And I'm glad I was able to acquire one of these. It's almost like it was ordained. Here you see the characteristics of a triode. What we looked at just a minute ago was the pentode section. This is a triode of a 6GH8 tube. If you look on the left at the pinout, you see it is, and I don't expect you to remember the 6U8, but take my word for it, it is exactly the same pinout as the 6U8. The 6GH8 was the replacement for the 6U8. It had a little more transconductance and could handle higher voltages. So the 6GH8 and the 6U8 that we saw a minute ago are both medium mu triodes. Mu just means amplification factor, and a sharp cutoff pentode. So these are what you would display for the triode section of that same tube. So let me show you a little bit about how the 570 is set up, and then we'll talk a little bit about how you might use something like this, though I will admit this is really just a boat anchor, okay? There is an application for it in tube matching for amplifiers, but frankly there are solid state versions of these kinds of things that can be done, and they work better because they work on a computer, so you can log the data and analyze it better and so on. But for a dinosaur like me to come across one of these things is sort of the find of a lifetime. They are very expensive on YouTube. I saw one on eBay. I saw one that I looked for. And by the way, the UPS delivery man and I had quite a long discussion. And several times I said, "Do you realize how much these might be worth?" And he said, "Yeah, but I just don't want to pack the thing up. So if I could just deliver it, that's what I would like to do." And sure enough, he showed up with it, and my one of my dreams of a lifetime came true. So I said I'd get away from me. Let's get back to the 570 and a little bit about how you set this up. Here is the rat's nest, patch cords, whatever you want to call it, that you set up a tube with. Along the top, you see, are a series of binding posts. On the left are 2 for heater, same on the right. Let me move this, turn this to get a little better light on that. There we are. Then there are crowns for the cathodes, and notice these are symmetric. Then there is grid A and grid B. There is a minus voltage that you can apply to bias the tube. There is a plus voltage, and this is the one place where they are it begins to be asymmetric. There is a plate connection, and there is a minus DC connection. So what are all of these for? Well, the grids are the step voltage that we talked about earlier. The plate is where you read the plate voltage and the plate current. The DC plus is to allow you to bias the screen grid, for example, of a pentode tube. And the DC minus is in case you need to bias a pin on a tube to a particular level, as well as the minus 150 27K, which has a kind of special function that I'm not sure if I'll get into all of that. But on the face of the 570, on the right, let me get a little more light on this. Well, something like that. You see on the right here is a voltmeter that you can select, and down below is what it shows, and it allows you to adjust the heater voltage, the positive and negative DC voltage, as well as the range of the meter. Then, below that, let me readjust this tripod. Beneath the meter is the step generator, and you notice that it allows you to either do 120 or 240 steps per second, and you can adjust with the red knob the number of steps per family. I'll show you that in a second. On the right is the volts per step and the start adjust, in other words, where that step voltage starts. Normally you want it to start at 0. And you notice that there is a little 0 marking right here where this is set right now. Beneath that is the CRT display. It adjusts the vertical and horizontal sensitivity as well as the vertical and horizontal position down here. Moving to the left, pardon the moving the tripod here, you see at the very bottom is the adjustment for the minus DC voltage. Above that are the operating voltages. You can set the heater voltage for anywhere from about 1.2 volts up to, I think it's 117 volts. So a pretty wide range of heaters, and it is adjustable. So for example, you can run a tube at below or above its normal heater voltage to see what that does to the characteristics. This is the control for setting the positive DC voltage, like for example the screen grid. It has both a step and an adjustable. And by the way, this is sort of the traditional Tektronix layout they used for decades. While this is a specialized oscilloscope, the bread and butter of Tektronix were their general purpose oscilloscopes, and they used this same basic control setup. So once you learned how to use one tech, you could use another. Above that is the plate sweep generator that you notice allows you to set the peak volts up to 500 volts and to adjust the size of the series load resistor. Finally, over here is the mains on, which we will now turn on. And you notice a little bit of a sound from the fan. Then you can turn on the test voltage. And the reason for this switch is so that there is no voltage on this test panel until you're ready for it. So, in other words, you don't have to move these wires around while there's voltage on the test panel. So now we're going to turn the test on, and you may notice up here on the meter, it now shows 100 volts is the plus DC voltage, and I have it set to the plus DC position. So now let's move this tripod up a little bit, turn off some of this light, and turn up the intensity, and turn on the grid A. Then, and what I'm doing is I'm flipping this switch down here from the grid A position to the grid B position. I know you can't see that because of the glare from these pilot lights, but here is grid A, that's one tube. Here is grid B, and you notice there's a setting in between for 0. What that is doing is switching between the grid of this tube and the grid of this tube, or in the case, if you wish, you can have two grids of the same tube, like a dual triode, where there are two triodes in the same section. And it all depends on how you have these wires set up. So that is basically how the 570 works and how you operate it. I'm not going to go through an extensive, showing a bunch of different tubes and all of that. I'm not sure what purpose that would serve, though I do realize a few people might be interested in seeing their favorite tube on a 570. But instead, what I'm going to do is talk a little bit about some small changes that I made to this 570 that improved its performance a little bit. And one thing, of course, it needed a cleaning, and I cleaned out the interior pretty well, vacuumed out as much of the dust as I could get, cleaned the tubes off, and did a pretty good cleaning on the switches and other things. Basically the same thing you do anytime you're restoring a vintage piece of equipment. Other than that, the unit worked right off the bat. So, but it had a few quirks, and fortunately, I was able to find and remember a few of the little changes and things that people had done over the years. And one of them I'll show you on the schematic. Tektronix normally did a wonderful job. In fact, their equipment was over-engineered. But on this 570, they did make one little design error, and so let me show you how I fixed that. And since then, this unit has performed beautifully. This is the schematic of the step amplifier. In other words, the amplifier that takes the step voltage and buffers it, amplifies it, and provides it to the grid A, grid B switch that you see here. So let me zero in on this part of the schematic. So this is the final power stage of the step amplifier. It consists of a 6 CL6 pentode And you may notice that the plate is driven directly off the minus 400 volt unregulated supply, and the cathode is driven through this 120K resistor from the minus 300 volt unregulated. So plus 400 on the plate, minus 300 on the grid on the cathode resistor. And then this is a cathode follower. So the signal comes out of there and is switched by this grid A, grid B switch to the grids of the tubes. Well, one of the problems that this stage has is the unregulated supply is located a long way away from this 6CL6. And because it does draw fairly high currents, it can oscillate. Now, early on, I think the tech engineers thought that the oscillation was due to parasitics in the test panel, the patch panel. And so they released some resistor jumper wires to try to suppress that. And that still does sometimes happen with certain particularly high gain, high frequency tubes, tubes used, for example, at UHF frequencies back in the day. But the real problem with this was the decoupling of the minus and plus unregulated supplies. So all that I needed to do was to add a capacitor very close to this tube from the minus regulated, and I used a 0.22 microfarad. You could use a bigger or a smaller one, just be sure that the voltage rating is sufficient, between the minus supply and ground and the plus supply and ground. And that cleans up the what appears to be oscillation on the grid signal, which of course also appears on the plate. Once you have changed the circuit to do that, this particular unit worked perfectly. Now there were a few other little issues with the 570. One I've already mentioned, the fact that some tubes would oscillate, and that you could help that by suppressing the grid. Let's go back to this picture here. The connection between this point and the grid could be replaced by a small resistor patch cord that would, it's basically called grid suppression, and the resistor is often called a grid suppression resistor. It was a common way of getting rid of parasitic oscillation in tube circuits. It's still used in transistor circuits today. There are times, particularly with MOSFETs, where you have to insert a small resistor in the gate lead to keep the stage from oscillating. But except for those couple of small things and a little bit of maintenance and a little bit of recalibration, I was able to get this 570 to work, and it was pretty much working when I got it. It just needed a little perking up, don't we all, at our age? So, I think what I'm going to do, I did want to mention something that, before I finish, and that is that the plug-ins that it comes with a pair of octal plug-ins. I'm using the 9-pin plug-ins right now for the tubes that are in there. It comes with a pair of 7-pin plug-ins. It of course comes with a series of patch cords and things of that sort. But one thing it doesn't come with is a way to do the characteristics of octal tubes. Now back in the day, the most prominent tubes were octal, 7-pin, and 9-pin. But Philco, partly just to get around patent restrictions, came up with a tube type that they called a loctal Let me show you one of those here. It looks like this. Notice that there's a small indentation there in the locating pin. Other than that, it basically is an octal tube. These pins are smaller physically, but they're the same 8-pin configuration that but there's no way to test these or to display these characteristics on the 570. But there is an easy solution to that, and that is if you take a let me get one of these over here. If you take an octal tube base that you can buy, these are very readily available today, and you pair it with a loctal socket. Now all that's inside this is just a wire from that pin to that pin, all the way through. In other words, 8 wires just going straight through from side to side, and then pulled through on the other side and soldered. But what that allows you to do is to test loctal tubes, which sort of completes the collection from the day. Now, if you want to test newer tubes, you can do so. The problem is that the most pins that any of these sockets have is 9 pins. So if you try to display a compactron, for example, you're going to run out of pins if you try to connect all of the pins of a compactron, because that has 12, or a Novar, that has 12 pins, and there's only a total of 9 pins available on the 570. But you can still do it using this same technique. You just need to be clever about, or frugal maybe, in the way you use your connections. So that is my experience with the Tektronix Type 570 characteristic curve tracer. I hope you've enjoyed this, and I hope you've enjoyed my other videos. At any rate, I do hope that things will go well for you in the future, and look forward to getting through this corona thing. Civilization will endure, and so I know that there are happy futures ahead. At any rate, for now, I want to say thanks for watching.